So this is the last of the reactions involving addition to a double bond, and it's really different than the other ones. It's called ozonolysis, and what it does is it cuts the double bond in half. It does what we call cleavage, and so it gives you two different products, or it breaks the double bond, so it gives you two different aldehydes or ketones, which is interesting, and it can be a little bit complicated. So in the overall reaction, it's called oxidative cleavage. Ozone is there's two steps. The first, and we're going to go over both of them. The first step, ozone is added, that's O3. And then the second step is a reducing agent, which is typically dimethyl sulfide, which is called DMS. And what it does is you take your alkene and it cleaves, it totally cuts the double bond, which is where the pi bond is, and it makes two separate products in this case, and each of the carbons becomes a carbonyl. So the one on the left here would give you a ketone because it has two other carbons attached. The one on the right here would give you an aldehyde because it has one other carbon attached. And it does have a hydrogen here, which your book typically doesn't draw the hydrogens in the aldehyde, so I followed along with that. I think it makes the aldehydes a little bit easier to spot. Just a note about ozone. What is ozone? Ozone is O3, and it's made of two separate resonance structures. So in the resonance structures, you can draw the double bond on the left and the single bond on the right, or the double bond on the right and the single bond on the left. And these have formal charges. Actually, there's the formal charges. So the oxygen in the middle has a plus charge, and the single bonded oxygen has a minus. So the actual ozone structure is a 50-50 mixture of these two resonance structures. So you can draw the mechanism for the first step, and it does this concerted reaction. A concerted reaction is where two bonds are breaking or forming at the same time, and it makes this cyclic ring structure, which doesn't stick around very long. It rearranges. So that rearranges really quickly to make this guy here, and we're not going to talk about the mechanism of this rearrangement. It's concerted, and one of the oxygens sort of flips over to the other side. So this is called an ozonide. You could stop here, and you can make these and put them in a bottle. Not very often. People don't do it very often, but you could. This is called an ozonide. And then the next step is you add a reducing agent, and the typical reducing agents for these, and you should know these, are DMS, which is dimethyl sulfide, or zinc mixed with water is another reducing agent for this. There's lots of other reducing agents too, but these are the two that are always used, pretty much always used for this reaction. And then you see that the two carbons, this carbon here becomes a ketone, and this carbon here becomes a ketone. Because this is a symmetrical double bond, both the carbons are the same, it's going to make two of the same product here. So this is a pretty quick reaction to learn, but it turns out you can use a lot of practice. It can be a little bit tricky to get the hang of both. We're gonna go forward and backward for these practice problems. In the first page here, we're going to go forward, where you're given the reactant and the reagent, which is ozone, and you need to draw the product. What are you going to make when you do both of these steps? Don't draw the middle step, just draw the final product. And then on the next few pages, we're going to do what I think is a little bit trickier, and that's where you're given the product and you have to figure out what the starting material looked like. So go ahead and shut off the video, take some scratch paper and do these on your own, and then turn the video for this page back on, and then we'll do the next page. So in this alkene, it is symmetrical, so it's going to make two of the same product. It's going to cleave the double bond, and what I did here was I marked in blue, I marked where the double bond is going to get sliced, so it makes it easy to see what the products are going to be, and this is going to make the two aldehydes, and they're both the same. So if your double bond is in a ring, and this happens a lot, we really like these. Again, you're gonna, the blue pen marks where we would cleave the double bond, and then both of these carbons are gonna be aldehydes, but because they're in a ring, there is only one product. So this carbon and this carbon are the carbons that were attached to each other, and they're still sort of, we say that they're tethered together in a ring. So here's another ring, and which gets cleaved here, but now the two carbons in the alkene are not the same, they're not symmetrical. So one of them is going to be a ketone and the other one's going to be an aldehyde. But again, it makes a single product where everything is joined together. Okay, this one's the most complicated. It has two alkenes and they're both going to get cleaved. So this one here in the ring is going to make the two ketones. They're going to be tethered together. And then this double bond here is also going to break. So this carbon's going to be a ketone. And then you're going to have a little 2-carbon product over here with an aldehyde. So that will give you two different pieces. Both double bonds would break. Okay, so in the next couple of pages, you are given the product, and you have to go backwards and figure out what the starting material would be. And I want you to be careful here to count the carbons. So this starting material has 10 carbons. It's C10, H16. And the product here has 1, 2, 3, 4, 5 carbons. So that tells us that this was cut in half. And for every reactant, there are 2 of these. And I want you to figure out what the reactant would look like. This definitely can take a little bit of time. I would recommend numbering the carbons and then go back and figure out what the reactant structure had to look like. Shut off the video while you do that and take your time, and then turn it back on and look at the answer. So it had to be a ring with 2 double bonds because it has 2 ketones in the product, and the starting material had to look like this. And it always is easier when you see it yourself. Going backwards this way, I find this a little bit tricky. So here's another one. It's kind of similar to the last. Again, count the carbons, both in the reactant and the product, and number the carbons and go through and figure out what the starting material had to look like. Stop your video and take a few minutes to do it, and then turn it back on. Okay, so when you count the carbons, you see that it had to be in a ring, and if you number the carbons, you can see that there must have been an alkene which joined carbons 2 and 6 to each other. So this is the starting material that it looked like. Okay, last one. Again, stop your video, go ahead and do it on scratch paper, and then turn it back on and see how you did. Okay, this one I didn't number the carbons because there was only one ketone. If you count the carbons, this starting material has 10, and the product has 5, so it's going to make 2 of these, and the double bond's going to be here. This one's a little bit easier. The last one was pretty tricky. And this is what the starting material looked like.